The Guadalupe Mountains of the western United States expose the remnants of a vast carbonate shelf that developed in a shallow Permian Sea some 250 million years ago. Today, rising over 1,000 meters above the desert floor at El Capitan, the widely exposed limestones of this shelf provide a wonderful opportunity to study a fossil reef, the Capitan Reef, that grew along its margins. However, interpreting such biologically influenced deposits is no easy matter, because the key witnesses to their production, such as these calcareous sponges and other such shelly organisms, are long dead and gone. To illustrate how our ideas can change, we'll start with the view that prevailed when we first filmed the Capitan for the Open University in the early 1980s, and then go on to see how that interpretation has been modified. For comparison, let's first look at the basic layout of a modern barrier reef typically built largely by corals. Three zones can be distinguished. First, there's the reef itself with its crest at sea level. Most modern barrier reefs face out onto open ocean and are fronted by a steep wall that plunges down towards the forereef zone, where debris that's spilled down from the reef accumulates on a submarine scree slope. Behind the reef, there's a back reef zone of lagoons in which water depths rarely exceed a few tens of meters. On the reef itself, corals and many other associated organisms thrive in the clear, warm water that surges over them from the open sea. Light is an important requirement, as the coral polyps rely heavily on tiny symbiotic algae in their tissues to supply food and recycle nutrients. Behind the reef, the more sheltered conditions favour the accumulation of fine-grained carbonate sediments. The monotonous surface of the lagoon floor hosts a relatively lower diversity of organisms, though scattered patch reefs may contain richer associations. Returning to the Capitan Reef, what's so splendid about this particular fossil example is that not only is there plenty of outcrop, but the original topography has been preserved, much as it would have been beneath the sea in late Permian times. The ridge on the horizon represents the shelf margin, while the dusty plain in the foreground was the site of a deeper marine basin, the Delaware Basin. In late Permian times, this basin occupied some 10,000 square miles of West Texas and was originally largely surrounded by the carbonate shelf that crops out today on its northwestern side. These shelf limestones form a mountainous plateau region in the southeast corner of New Mexico, to the left here, and the original shelf margin is marked by the escarpment running off into the distance that drops down into the Delaware Basin on the right. The prominent cliff face running off to the left in the foreground is a later feature created by faulting. Canyons cutting across the escarpment and opening into the basin beyond provide several natural geological sections across the shelf margin. One in particular, McKittrick Canyon, provides an excellent profile through the main structure of the Capitan Reef. High up in the back of the canyon are more or less horizontally bedded limestones that accumulated on the shelf area behind the reef. The large cliffs high above the mouth of the canyon represent the reef rock itself, and to the right, 4 reef beds sweep down into the former basin. Now, there's a pretty clear distinction between the more or less flat strata of the back reef on the left, massive limestone of the reef itself in the middle, and the foreslope strata, which are dipping down towards the basin on the right. And that's pretty much the sort of pattern you'd expect to find if you took a section through a modern barrier reef, so the analogy between ancient and modern seems to be holding up, in broad terms at least. But what about the reef rock itself? How does that compare with its modern equivalent? What I'm walking across is part of the ancient reef itself, preserved here as massive limestone. In most places it's been heavily recrystallized, so you can't really see what's going on. But here and there are patches where the fossils are very well preserved. For example, this is a section across what would have been a large mound-like sponge. And down here are a number of sections of what would have been leaf-like algae projecting up from the reef surface. These, with other organisms such as bryozoa, grew up from the reef surface to create a kind of framework for its growth. Meanwhile, everything was being densely encrusted by these successive light and dark bands down here. This layering is more obvious when seen in thin section under the microscope, though here the dark layers correspond to the thin light bands seen at the outcrop, while the thicker dark grey bands at the outcrop are represented by the pale, transparent layers in the thin section. The dark bands seen here are thin encrustations formed by calcareous algae, whereas the transparent bands are thick crystalline crusts of calcite cement. The cement must have grown at a very early stage, close to the surface, to have allowed the occasional intergrowth of algal incrustations. In addition, there's quite a lot of incorporated fossil debris in the rock, such as this gastropod shell, derived from the abundant fauna that lived on and around the reef. From such outcrops, we can try to imagine what the original reef must have looked like in late Permian times. This spectacular life-size reconstruction of a part of the Capitan Reef was built for the Permian Basin Petroleum Museum in Midland, Texas in the 1970s. It suggests that the variety and abundance of life on the reef were probably just as great as on a modern reef, and that its basic structure was also similar, though with rather different actors in the same roles. Though, in striking contrast to modern reefs, there are no large framework building corals. Instead, calcareous sponges are particularly abundant. Fern-like bryozoans are also very common. As are the distinctive crinoids commonly known as sea lilies. These, together with a variety of brachiopods and other shelly organisms, also provided debris which was eventually incorporated into the reef rock. So did this reef grow in the same kinds of physical conditions as a modern tropical barrier reef? Let's first of all consider the salinity. The organisms of the reef are strikingly varied, but there are a number whose living relatives are only found in marine water of normal salinity, such as the crinoids and articulate brachiopods. Otherwise, of course, the abundant algae show that the water over the reef was well lit. So it's reasonable to assume that, as with modern tropical barrier reefs, the Permian Reef was bathed in open, well-lit seawater. But what about its resistance to wave surge? Most of the framework organisms in modern reefs, like these elkhorn corals, have considerable strength and rigidity. They protrude right up into the shallow zone of wave surge. Occasionally, though, they do get broken up during violent storms. A few kinds of living corals otherwise cope with wave surge by being flexible. And so the question we need to ask is, did this reef have the same sturdy framework that characterizes modern tropical coral reefs? Do you imagine that the main framework organisms here could have withstood battering by waves? Many geologists now believe that the answer is no, and this means that the reef would have grown below the level of wave action. In front of the reef zone, beds of reef debris slope steeply down into the basin, where in late Permian times the water must have been at least 600 meters deep. This knobbly bed of limestone here is a lens of what would have been loose reef debris that slithered down the slope in front of the reef. and came to land on the finer grained sediments at the foot of the slope. Now, those finer grained sediments have been compacted a great deal more than the limestone, so this is why they appear to be bent around its base. Now, we're some 600 metres down from the level of the reef itself, but even down here there's still an abundance of large whole fossils. Some of the shelly debris was transported in, but in situ material is also present. The fossils are quite easy to see because they've been silicified and are more resistant to dissolution than the surrounding limestone. There are plenty of sponges and brachiopods and even scattered crinoid ossicles. Such bioclastic debris is quite similar to what one might find on the upper forereef slope of a modern reef. A short way further out into the basin, the fossils are far fewer and smaller. In this small cliff of limestone with chert nodules here, they're restricted to certain horizons. For example, there are a number of small entire brachiopods which may well have lived down here, and otherwise small fossil fragments which probably drifted down from higher levels. And as soon as you get further away from the shelf margin into the basin proper, the scenery flattens off quite dramatically. In this kind of flat terrain, your only chance of a decent outcrop is the occasional road cutting such as this. I'm about 5 miles out into the basin, and already the beds here are much thinner and more or less flat. They're made of fine muds and silts, and they're extremely finely laminated. Of course, this means that they haven't been churned around by burrowing organisms. Moreover, body fossils are extremely scarce, just the occasional sponge spicules, for example, which have been drifted down from higher levels. So life out here on the basin floor must have been very scarce. The basin wasn't completely enclosed by the shallow shelf, as there were a few openings to the open ocean to the south. As a result, well-aerated oxygen-rich water was brought in and circulated around the upper part of the basin. But the general lack of fossils away from the shelf margin suggests that the deeper waters in the basin remained anoxic. We've taken a look so far at the deposits of the reef itself and those of the forereef and basin. But what about the shallow submarine shelf area behind the reef? Here there are flat-bedded strata, mainly of carbonates and evaporites, that thin towards the ancient shoreline, which was still at times up to 50 miles or more further north into New Mexico. I'm now about 30 miles further along the escarpment to the northeast from McKittrick Canyon, and I'm on the very back part of the reef. The massive limestone of the reef here consists of patches of bound limestone with intervening areas of coarse shelly limestone, which would originally have been well-winnowed shell sands and gravels. So clearly this back part of the reef was rising up into very shallow water where there was abundant wave current activity. But what about further up on the shelf, immediately behind the reef? Here there's a belt of thickly bedded grainstones formed from loose aggregates of washed-around carbonate sands and gravels. Thin sections show mainly fossil fragments, or bioclasts, surrounded by clear cement. And there are also plenty of nearly complete portions of crinoid stems. Because they're not very broken up, it's probable that they were snapped off from live individuals during storms and quickly buried nearby. Crinoids will only live in water of normal marine salinity. So even though we're behind the reef zone here, this outer part of the grainstone belt was evidently still bathed in open seawater. Even further back behind the grainstone belt, we reach sediments deposited in shallower, more restricted conditions. Fossils here are scarce, and of organisms such as this gastropod, which could tolerate high salinity. These outcrops contain a variety of rock types, including these laminated limestones which were formed by algal mats. The tiny cavities in the crinkled layers are believed to be fossil gas pockets produced by rotting algae in an intertidal setting. So the area had variable salinity and was also sometimes emergent. Behind this barrier were shallow lagoonal waters where intense evaporation led to the precipitation of evaporites. Bedding sometimes became buckled with the growth of the evaporites within the sediment. We're now in a position to compare the Capitan with a modern barrier reef. In the Permian, wave energy was evidently largely dissipated over the grainstone belt behind the reef, though wave base itself need not have been particularly deep, given the small size of the Delaware Basin Sea. Further back on the shelf lay the barrier of islands and shoals. A modern ocean-facing barrier reef presents a rather different profile. Here, the impact of wave surge, often of considerable strength, is largely absorbed over the shallow crest of the reef itself. So even though the modern and ancient reefs show broadly similar zonations, in detail there are some important differences in the circumstances in which the various facies formed. Evidently, therefore, we can't interpret fossil reefs such as the Capitan simply by forcing their constituent facies into a general model based on coral reefs today. Instead, our interpretation has been pieced together like a jigsaw, and the pieces of that jigsaw have been inferences about environmental processes and conditions that we've been able to draw from detailed observations of the rocks. Uniformitarianism applied to the particular rather than to the complex whole. Time has moved on since we shot that footage of the Capitan Reef. Indeed, the reef and I are both some 15 years older. Now, you might suppose that the reef has probably suffered rather less in that passage of time than I have, and in one sense that's true. I'm sure that those old Permian rocks in West Texas and New Mexico are pretty much the way we left them. But in another sense, they have seen an important change. It's a change in the way that we interpret the Capitan Reef. You see, science never stands still. All a scientist can do is come up with the most plausible model that reflects currently available observations. But if they make some new observations which refute the old model, then they have to chuck that out and come up with a new, more suitable model. And that's exactly what's happened with the Capitan Reef. Some new observations have quite literally turned our interpretation of it upside down. And that's why we've come to Cambridge to talk to one of the researchers who was responsible for this revolution. She's Dr. Rachel Wood, a former PhD student of the Open University, now based in the Earth Sciences Department in Cambridge. One of her main research interests is the geological history of reefs, and she has particular expertise with fossil sponges, so the Capitan was a natural candidate for her attention. Let's start with the observations. We got some of your field photographs here. First of all, where did you take these?
These field photographs are from McKittrick Canyon, which is more or less the middle part of the Capitan limestone. This is a field photograph of a vertical surface through the reef itself. So it's telling us something about the nature of the different elements of the community.
If we were in the field, we might be looking straight onto the side of a rock face like that.
Yes, exactly so.
Okay.
If you imagine you're staring at this rock in the field, the most obvious aspect are these structures, and these are calcified sponges. And of course, for a long time, the fact that these sponges are appearing more or less vertically was used as a reason to interpret the reef as a mass of sponges that grew upwards on the sea floor that somehow baffled sediment, and so the reef accumulated in that fashion. When you look at these sponges in detail, you can see that they are in fact upside down. And the way we tell is that these sponges have a chambered structure where they grow by adding a new chamber onto the pre-existing chamber, so forming a whole string of bead-like chambers. And you can see here a cross-section through one of these chambered sponges. Here's the older part of the sponge, and you can see here the growth direction of these chambers is in a downward direction. So this sponge, and indeed all of these, in fact, grew downwards into crypts.
Why hasn't this been seen before?
Two reasons, really. One is that the exposure of the Capitan Reef is relatively bad. A lot of the surfaces are very badly weathered, where you can't really see any detail of the ecology. In other words, you can't see sufficient detail to determine the relationships of the different ecological components of the reef. Secondly, obviously, to get a sense of the direction, you must have a vertical surface. If you have a horizontal surface, you won't have any indication of the growth direction.
So if they were upside down, what were they attached to?
Yes, that's the big question. Well, here's a second photograph, also of a vertical surface, and it clearly shows what some of these sponges were attached to. Here you can see a series of these downward projecting sponges, and these two are clearly attached to this row of dotted points. And this is a cross-section through the lattice work of a fan-shaped or frondose bryozoan. If we just turn to a third field photograph, the grey material was previously interpreted as some sort of sediment that infiltrated through the open framework of the Capitan Reef and slowly filled up the base of the cavities. But you can see here that it clearly has a very, very different origin. This is a field photograph, perhaps twice life size.
Vertical again?
Again, it's a vertical surface. And you can see that this grey material has an encrusting quality. You can see it's very finely laminated. And here are two cryptic, downward projecting calcified sponges. This one is attached to one of these frondose bryozoans. But you can see the whole mass has been coated and encrusted with this grey laminated lime mud material, both on the upper surfaces and the lower surfaces. And in fact, we think that this material, although it's of controversial origin, may have an organic origin. It's not a detrital sediment. It might have been produced by some sort of microbial community, something like a modern-day stromatolite.
And this brown material that's swirling around it?
This brown material is cement. It's a later stage part of the Capitan, but it's a very important part of the Capitan limestone because it accounts for between 40 and 70% of the total reef rock volume. This is an alternative reconstruction based on such field observations. So if you were a snorkeler in the middle part of the Capitan Reef, it would have looked something like this. You can see these frondose, these fan-shaped bryozoans projecting at all sorts of different angles, some of them vertical, some of them almost horizontal. And attached to the undersurfaces are these cryptic calcified sponges. We do have some idea that they all seem to align outwards into the oncoming currents. You can see there's some alignment of these sponges. So this is the basin, oceanward part of the reef, and this part here is the shallower part of the reef. So we have those two elements. You can see that they're slowly being engulfed by this darker grey material, which is this microbial community, this stromatolite-like community. So geologically, what we see are these cavities. These are cross-sections through these frondose bryozoans, the attached cryptic calcified sponges. The whole lot has become engulfed with this grey micrite material. And then finally, the final stage, the growth of these cements, which are these rather attractive hemispheres with very large crystals, these botryoidal cements, which would have eventually occluded the whole cavity space.
Do you get calcified sponges like this around today?
Yes. In fact, with the advent of deep-sea diving, it's become possible to dive to fairly considerable depths. And in fact, these sponges have only been known for the past 20 or 30 years since it's been possible to dive into deep caves and grottos in modern reefs. These are calcified sponges growing from the ceilings of a modern-day grotto or cave within a living coral reef, and they grow at considerable depth. You can see a mass of these calcified sponges which have grown attached to the ceiling of a cave.
Most of the biota you have interpreted as having lined the roofs and the walls of these cavities, and so far you've only mentioned the frondose bryozoans as being possible primary framework builders. Were they the only ones, or were there others?
The Permian Capitan Reef, like a modern reef, was in fact a mosaic of many different communities. And, for example, here's a reconstruction of another community type. We know that there were at least perhaps 5 or 6 different types of communities that contributed towards the Capitan Reef. And this is a community which has a radically different ecology to that of the Frondo's Bryozoan. In contrast to the previous one, which was dominated by animals, this is a community dominated by plants. And in fact, this is dominated by algae. Now, this particular reconstruction isn't exactly of the Capitan Reef, it's of something similar. And the area I want to concentrate on are these green lettuce-like forms. These are known as phyloid or leaf-like algae. So what you see in geological section are various cross-sections through these very fine leaf-like algae, which became progressively encased with cement that probably precipitated fairly early on in the history of the reef.
What is the implication of this reinterpretation for the environment in which the reef grew?
One of the striking things about the Capitan Reef, in fact, about many Paleozoic reefs, is just how much of the framework is actually in situ. And this is in stark contrast to a modern coral reef, because if you're a snorkeler looking at the living community of a coral reef, you see all these in situ frame-building organisms, corals mainly. If you were to drill a borehole through the surface of the reef, what you would find is between 40 and 90% rubble and sediment. And this is for 2 reasons. The reef becomes destroyed, firstly by heavy wave action and storms that occasionally will rip through a reef and reduce it to rubble and sediment. But secondly, an intrinsic part of the ecology of a modern reef are organisms that gouge and etch and variously bore into the calcareous skeletons, so reducing them to rubble and sediment. And many of those organisms that are so important to the ecology of a modern coral reef system simply hadn't evolved by the late Permian. And as a result, a lot of our Permian communities, indeed many Paleozoic reef communities, are more or less intact. The framework hasn't been destroyed.
At the broadest level, then, to what extent can we use modern reefs to explain fossil reefs?
Well, the principal conclusion is that where biological communities are concerned, we simply can't use the present as the key to the past. The Permian Capitan Reef clearly grew under quite different ecological and environmental controls to those which modern coral reefs grow under.